Hello everyone, welcome to Analog Electronic Circuits experiment number 3. So in today's lab, we have to study the frequency response of MOSFET amplifier. So here is the MOSFET amplifier given to us and we will be start implementing it directly, right? So I have opened up the LTspice window prior only. So let's start building up the circuit now. So I'll go to the library, select the NMOS. I can select NMOS. This is the N-channel MOSFET transistor. I click on OK and I place it onto the screen. Next, I have to connect the resistors and the capacitors in the circuit, right? So for that, I'll slightly minimize and then I'll add a resistors over here. So we'll add resistors over here, right? Quickly. And one resistor we require over here as R6. Yes, and one is for RL. So we have added all the resistors required in the circuit and now we have to connect them together. We'll use the wire and connect all the resistors together. Okay. This is R6. Actually, your capacitor CC1 will also come. So I'll wait. Now I require the capacitors, the coupling capacitors and the bypass capacitor. So I can select the capacitor from here. I can add the bypass. Here I have to rotate. So I'll press Control R. So here I've added all the capacitors over here, right? Now I will require a DC power supply and the voltages also. So I'll go again. I'll go to voltage. I'll require a DC voltage over here, which I will place it. Here I'll require a AC voltage. So now all the voltages are also added. Now I'll do the connections quickly. Here we will add the ground for the DC supply. And now we will do the connections for the remaining part of the circuit. So here is I'll connect to the load. And here the bypass capacitor is connected across the RS register. Yeah. And last thing is the connections over here. So I'll use a wire and connect them right through the AC supply. Okay. Yeah. So that is connected. Now I'll require the ground also. So don't forget to add the ground. That's the most crucial part. Okay, so the circuit is ready. Here also I'll add the ground. Yeah. Now circuit is complete. Now we'll fill the components one by one. This will be R6. Okay, internal resistance of the voltage source. This is my VS, right? And right now we want to do the frequency response. So for the frequency response, we'll give the AC amplitude as 1. Okay, and then click on OK. Fine. The resistance value R6 is 1 kilo ohm. Then we have coupling capacitor CC1. That value is 1 microfarad. Then the DC power supply is VDD. And its value is how much? 5 volt. So I'll right click, add 5 volts and press OK. Now this is register R1. So I'll call it as R1 and its value is 100K. Okay. So I'll give the value quickly over here. This is R2 and its value is 20K. Fine. And this is RD, drain resistance RD, and its value is 5K. So I'll right click on the value and put it as 5 kilo ohms. This is RS. RS value is around 1 kilo ohm. So this is 1 kilo ohm. Then this is output coupling capacitor CC2. Its value is 2 microfarad. So I'll give it as 2 UF. That will be 2 microfarad. Then this is CS and its value is 10 microfarad. Okay. And finally we have RL. We have RL over here. Name it as RL and its value is 10 kilo ohm. Fine. So the circuit is complete now. Now we have to add the dot model over here, right? Dot model parameters. So what you will do is you will right click over here and name it as NMOS1. Okay. Also, you can rename this M1 transistor as M1 underscore your name. Okay, so that all the plots which you get, it will have your name so that you can take the print screens easily. Now I will label the input and output. So over here, I'll right click. First of all, I'll extend it a wire outside a little so that you can represent that node properly. Yeah. So I right click, add on the label net. Then I'll add over here V in, or you can call it as V in underscore the name. Okay. So here when I add it, I can just make it an input port. I forgot to do that. So I'll call it as V in underscore your name. And here I can write input. Okay. So this will be my input label. Similarly, I will add the output label. So I can copy this thing. And this I will call it as output. Okay, fine. So this is the V out actually. So I call it as V out. Now my circuit is ready. I have to add the model parameters. So model MOSFET parameters are Kn, VTN, WL, and lambda. So I'll right click, go to draft, go to spice directive, and over here I will write these parameters. I'll write dot model NMOS1 because that's the name which we have given. Then the reserve word NMOS bracket. Kn is written as Kp inside the model. So 1 e raised to minus 3. So 1 e minus 3. Okay. Or you can write 1 milli also. That will also do. Space VTN. So that is called as VTO in the spice model. It is 0.4. Then we have W, which is 2 micrometer. So we'll add W is equal to 2U. Okay, 2U means micrometer. Then L is equal to 1 micrometer and lambda is 0. So we'll substitute lambda is equal to 0. So then we press OK. So this dot model will appear onto the screen, right? Also, they have given parasitic capacitance CGS and CGD, right? So internally inherent, the parameter, the capacitance are present. Now, since we are defining the model ourselves, we have not defined the parasitic capacitance inside the model, but rather just to show the picture that these are the inter-electrode capacitances connected between the terminals. We can externally connect them, but with a very small value. So let me add these two capacitors over here, right? So one will be CGD. Okay. So let me add over here. This will be CGD and this will be CGS. Okay, so here this capacitor, I'll rotate it and then I'll add. That will be better. Yeah, let me add this capacitor by rotating it and adding it over here. Okay, so here I'll connect it with a wire. So this is my CGS. So let me rename it as CGS. And what's the value given to us? 20 picofarad. So its value is 20 picofarad. This is just to get a feel that there are inter-electrode capacitance is present. Now we have not used any model which is an industry standard. We have defined our own model. So that's why we have to define these parasitic capacitances. We can also show wiring capacitances, but here only the parasitic capacitance are given. CGD is 0.2 picofarad. So here I will write, I'll right click. This is 0.2 picofarad. Okay, so this value I will push it aside here. Okay, so I'll continue now. Now this name I will give it as CGD. CGD. Okay, fine. So circuit is ready. And now we have to do the frequency response, right? Now let's me come back over here. So for the frequency response part, what we will do is we know that the gain of the amplifier is given by AV, and that AV is V out upon V in. Now in this case, it is VS, so it's fine. V out upon V in is, so if we substitute the input VS, right? If we substitute the input VS, now let me change it to, just wait a minute. instead of writing it V in, we can write it as Vs. So if we make Vs equal to input equal to 1, then we can say the gain is output only directly, right? Gain is actually the output. So that is what the strategy we are using over here. So part 1 is common source amplifier with bypass capacitor CS, and part 2 will be the common source amplifier without bypass capacitor CS. Okay. So the first frequency response plot, you have to do it for the with the bypass capacitor. So that means I have to change the frequencies in such a manner that for these frequencies, I'll note down the output voltage and the voltage and the gain in dB. So in this case, in the first case, we will take the value of Vs, will take the value of Vs as 1, okay, as 1 volt, and then we will varying the various frequencies. So that is the assumption which we are going to use. We'll take the value of Vs as 1 volt for common source amplifier with bypass capacitor, and these are the frequency ranges. So you also have to note down the gain in dB. So for that, what we will do is I will maximize the screen. So for AC, for frequency response, you click on run and click on AC analysis. Here the type of sweep selected as decade, number of points you can put it as 100, start frequency you can put roughly around 10, and end frequency will be around 100 megahertz. So megahertz is written as capital MEG in SPICE. Then click on OK. So your semi-log scale will appear. X-axis is log and Y-axis is linear. So over here, we'll right click and add trace. We'll plot V out. Okay. Why do we plot V out alone? Because the reason being, we have already discussed this over here. Let me just clarify it one more time. We plot only V out and it's the gain because Vs is 1. Okay. So slightly the graph is starting from here. So let me start at a lower frequency, right? Like 1 hertz. So I'll change it to 1 hertz now. Then I'll simulate again. Yeah. So here is the graph which I'm getting. Now this is the phase plot and that's the magnitude plot. I don't want to see the phase plot. So I right click and delete the phase plot. So here is my frequency response graph. If I take more readings, then I'll get even more better graph, right? So let's say if I take till 500 megahertz, let's say that 500 megahertz. Yeah. So this is the frequency response plot, as you can see. Now, for this, from this frequency response plot, you have to take the readings. You have to take the following readings as follows. So at input signal frequency, let's say around 500 hertz. Input signal frequency of 500 hertz. What's the value of the gain in dB? Okay. So that is what we are noting down over here. So let me show it to you the cursor. Okay. Let me keep the cursor over here. And we'll check the value now. So I have to check the value at around 500 hertz, let's say. I mean, I can take it at extremely low frequency. In this case, it's starting from 1 to 10, and then it goes to 100 also, right? So what I have to do is to collect this reading, I have to do some modifications over here, right? The low frequencies are too low, so I have to start with 1 hertz onwards. Okay, no need to go till 5 megahertz. So what you can do is, for extremely low frequencies, I can just push this table down a little bit down, and then I'll consider those frequencies again. Okay, so wait a minute, let me do that. Okay, I'll select this table and I push it down a little bit. Okay, so let me maximize the screen now. Okay. So what happens is I want to measure over here, as you can see, the frequencies are in hertz, right? So here what we can do is, one thing we can do is, if you want to keep it in 100 hertz or so, what you can do is you can increase the value of CS and check. So instead of 10 microfarad, let me give it as 100 microfarad. Okay, it will only disturb the low frequency response. I'll prove it to you. Yeah. So right now it's disturbing the low frequency response. So your curve is slightly improving. Yeah. So let me do that once more and change this to a lower value. Let's say 4.7 microfarad. Yeah, when I keep it 4.7 microfarad, now it's drastically reducing. So yeah, it's getting affected. As you can see, if I change my coupling capacitor or bypass capacitor, it changes. So let me change this to 0.1 microfarad. Let me change this to, let's say, 0.2 microfarad. And let me change this to 2.2 microfarad. Right? I'm changing the connected capacitors, coupling capacitors and the bypass capacitor. So that will greatly influence my frequency response. As you can see, it is influencing the frequency response. Now I can start from 10 hertz. Okay. Now I can start from 10 hertz or so, and I'll get a proper frequency response now. Yeah, here it is. Right. And now I will check the readings now. Let's say I'm checking the reading at around 100. Around 100 hertz approximately. Let's say what's the value. Yeah, so that value I will write it over here, around 100 hertz. Let's see what's the value it is coming. Then I'll write it over here. Let me add a blue color. Yeah, so what's the value? Around 411 milli dB. Okay, so it's around 411.44 milli dB, very small value. Okay, and then I will go, let's say, to 500, around 1 kilohertz, let's say. So at 1 kilohertz, the value is 6.16 dB. Okay, as you can see very clearly. Let me go slightly up over here. At 1 kilohertz, the value of the gain has increased to 6.166. Okay, sorry for that. Yeah, so its value is going to now 6.166 dB. Okay, we can write, yeah, like this. So at 1 kilohertz, we have 6.166. At 10 kilohertz, what do we have? Let's check it out. At 10 kilohertz, it's around nearby 6.25 dB. Okay, so at 10 kilohertz, its value is 6.25 dB. Now let's check at a higher frequency. Let's say we check it at around 10 megahertz. So this is roughly around 10 megahertz. Yeah. Okay, it's disturbing, changing, very sensitive it is. I can maximize the screen over here and I can adjust it delicately. Yeah, this is close to 10 point, we can write 0.5, yeah, 2.24 dB. So I can go over here, I can go to around 10 megahertz and I can enter that value over here. Okay, so I can enter this value at 10 megahertz. How much is the value? Is 2.24 dB. So it's falling down. So in this way, you have to take the readings for all the frequencies shown over here. Okay, starting from, you can even start from 50 hertz. It doesn't matter, right? As it fits you. So you can start with 50 hertz also and note down the reading. Okay, note down the reading of the gain in dB. right? Okay, all right. Now, from this graph, you can calculate the bandwidth also, right? So let me show it to you what the bandwidth will be. So you're getting this type of a curve, right? The frequency response is this type. So if you note down the maximum value, if you go 3 dB down, and you can note down FL and FH very easily. So FL is the lower cutoff frequency, FH is the higher cutoff frequency, and bandwidth is FH minus FL. So let's do that. Okay, let's calculate FL and FH. So over here, let's check the maximum voltage gain. It's 6.25 dB. So you have to go to 3.25 dB. So let's do that. 3.25. So it's 3.3. Let me maximize this part. 3.25 dB. Again, maximize it. Yeah. Yeah, 3.25 precisely. And it's happening at 152.45 hertz. So that's the value which I will write it over here. Its value is 152.46 hertz. So that's the value of lower cutoff frequency. Now to check the higher cutoff frequency, what you will do, you will again check it at 3, you'll go 3 dB down, 6.25 over here, 3.25. 6.25 minus 3 will be 3.25. So I'll maximize this part, 3.25. I can even maximize it further. Yeah, here it was coming properly. 3.25. It is 8.14 megahertz. So that's the value of your higher cutoff frequency. 8, let me rewrite it. 8.143 megahertz. Okay. So if this is coming as 8.143 megahertz, what will be my bandwidth? My bandwidth is FH minus FL. So this will be approximately equal to 8.14 megahertz itself. Why? Because compared to megahertz, the hertz value is very, very small. So that's why bandwidth is approximately equal to FH value itself. Okay. So you're getting around 8.14 megahertz at around 3.25. I mean the 3 dB down value, right? Higher value was 6.25. Let me cross check. Yeah, 6.25, and at 3.25, you are getting around 8.14 megahertz. So this is about the frequency response. Now, for this part, yeah, there are two parts in it. One is with the bypass capacitor and one is without the bypass capacitor. So for part 2, you have to repeat everything, but you have to remove the bypass capacitor. Okay, and you will observe that by removing the bypass capacitor, your bandwidth of your amplifier will increase. Okay, later on you can contemplate on that, why the bandwidth of the amplifier is increasing due to removal of the bypass capacitor. But that is a fact that will happen. Fine. So let's move on to the next point. Now we have to measure the voltage gain. I mean output voltage, right? So to measure the output voltage, what we will do is we'll again go back over here. Okay. Right now my input applied Vs applied is 1 volt. But in the transient response, we will apply around, let's say we will apply 1 volt itself, right? And right now, let's check the output voltage. So for checking the output voltage, we have to right click over here and click on logarithm and click on OK, right? So this will give me the output voltage as various frequencies. So let's check it out. Now at let's check it out at 100 hertz. At 100 hertz, the value is 1.067. Okay. At 100 hertz, the value of V out is 1.067. Fine with it? Yeah. And next we check out, that is magnitude of V out it is showing you. It is not showing you the this thing. Now let's check it out at 10 kilohertz. What's the value? So at around 10 kilohertz, let me check it again. at 10. Okay, here it is approximately 10, 2.053. Okay, so the value is 2.053. Next, we can note down the value at around 10 megahertz. So let's check it out. At around 10 megahertz, what's the value? So here it is approximately 10 megahertz, and the value of the output is 1.296. So we can write it over here accordingly. It is 1.296. Now remember, while we are writing this, we are assuming that the input over here, Vs, is of 1 volt AC value. Okay, and in a transient response, you also have Vs as 800 millivolt. So remember that you have to accordingly give the V out value over there. Okay, now this completes the frequency response of common source MOSFET amplifier with and without the bypass capacitor. Okay, so you have to note down, fill up this table of output voltage and gain in dB, and then you have to note down the bandwidth in each case. So bandwidth in case of without the capacitor you observe, and with capacitor you observe. Okay, now let's do the next part. Next part is this is the part B, that is FL, FH, and bandwidth. Next part is transient response. So that means we have to note down the V in versus time and V out versus time. So over here we will go for V in equal to 1 volt peak to peak. Okay, so here we'll see, here we'll do some changes. Instead of 800 millivolts, we'll give Vs source as 1 volt peak to peak. Okay, let me write it nearby. Vs will be 1 volt peak to peak value. Frequency will be 10 kilohertz, because as you observe around that 10 kilohertz value, so as you can see, if I close this and do it again, at 10 kilohertz value, the gain is almost constant, as you can see, right? So we can safely take that value of 10 kilohertz. Okay, and what we need to note down, we need to note down the V out theoretical value and simulated value, gain theoretical and gain simulated. Okay, and this has to be done with bypass capacitor and without bypass capacitor. So we'll take the reading number 2, right? So let's start doing it. So I'll go over here, close this, go to the circuit, and I have to do the following changes. I have to delete .ac, and then I again have to simulate, click on run. First, let me close the output waveform. Yeah, so I'll click on simulate, click on run, and here the stop time I have to give. Now, also before giving the stop time, I have to change the AC input over here. So here earlier we have given AC input because you have to vary the frequency. Right now you remove it from the circuit, and then you select a time, sinusoidal signal. Amplitude will, DC offset will be 0. Amplitude will be 1 volt. 1 volt peak to peak, so it will be 0.5 volts peak over here, and frequency will be 10 kilohertz. Okay, and then click on OK. So what this statement will do, this statement is for the applying the sinusoidal signal only at one particular frequency, 10 kilohertz, right? And we are checking the output. Now we'll click on the simulate, click on run. It will ask for the simulation command. You should select transient. What stop time will you give? So basically your time will be 1 upon frequency. That will be 1 upon 10K. That will be 0.1 millisecond. But let's say you want to observe 4 waveforms. So I will be 4 cycles. So I can give 0.4 millisecond and then click on OK. And now over here, I can maximize the screen. X-axis is the time. I will first plot the input V in. And then as you can see, it's 1 volt peak to peak. Then I'll plot the output. Okay. So I think it's slightly let me check. Okay, so as you saw now that the output is slightly clipping at the positive half cycle. Now why this is happening is because we have applied a very large input, right? So input it's around 500 millivolt, right? So such a large input will not be sufficient. So you have to give a smaller input. Let me give around 100 millivolt. So if I give 100 millivolt and then I observe the waveform again, it will be proper. It will be symmetric. Yeah. So that's what I'm getting. So I think we have to change the input over here. Instead of giving it as 800 millivolt, we will give it as around 200 and 400 millivolt accordingly. Okay. So let me give it as around 100 millivolt and 200 millivolt peak to peak accordingly. So here also instead of 1 volt will be too high value because it's distorting the output now. So I can give it over here as 200 millivolt peak to peak. 200 millivolt peak to peak. So for I think this is yeah, this is 200 millivolt peak to peak, and I'm getting my output amplified form, right? So this circuit over here is working as a MOSFET amplifier. Now I need to measure the output peak to peak value, right? Using dot measure statement, I can measure it like this also. The positive peak and the negative peak, I can check it out. But we will not use this procedure. We'll use a different technique. Okay. So we'll use a dot measure statement. So I'll right click over here, click on graph, click on spice directive, and I'll start typing dot measure. V in is the variable, peak to peak, and I'll write V of V in. Label I will write. Okay. So this is V in. This will measure the V in peak to peak value and store in the variable V in. Then there is dot measure V out peak to peak, V of V out underscore the name. Okay, this will store the value of output peak to peak in the variable V out. Then we have dot measure gain. We can calculate the gain also directly. So we'll write dot measure gain param V out divided by V in, and then we click on OK. Okay, so we have added this dot measure statement. Again, you simulate, maximize your graph over here. Okay, and then go to view and go to spice error log. So spice error log is giving you the value of the output. Now remember, input and output waveforms are out of phase. That means your gain is negative. Okay, whenever input and output are out of phase, the gain will be negative. And over here we are getting, if we simulate this again and maximize the schematic, I'll go to view and I'll go to spice error log. So here I'm getting the voltage gain as 2.05. Unfortunately, it shows only the magnitude. So this value I can write it in the this thing over here. Okay, it was showing 2.05. So that's the value which I can write over here. 200 millivolt peak to peak. So V out value theoretical is coming out to be minus 2.05. 4, okay, or 0.55 we can write like this volt. I mean, sorry for that, this is the gain actually. What's the V out value? V out value is minus 0.41 minus 0.41, and the voltage gain is the theoretical simulated value is coming out to be minus 2.0545. Okay, that's the value which I'm getting. Now I can verify it in the simulation. We will soon do that. So this is how we can measure the output value and the gain value from the graph. If you have a doubt, you can ask. Okay, so this will directly give me the gain, peak to peak value, output and gain directly. Okay, so this amplifier is providing a gain of 2. Now, next is we can check theoretically now how this gain is satisfied. Fine. So let's move on slightly up above. So we have to solve the DC analysis and get the value of GM. So that GM we can find out to calculate the gain. So if you do perform the DC analysis of this voltage divided bias, the VG value will be given by R2 divided by R1 plus R2 into VDD, right? And we got the value of VG as 0.833. Then VGS is VG minus VS. And what is the voltage VS given by? VS is IDRS, right? So let me maximize this part now. So basically I want VGS and ID. So over here we have, VGS is VG minus VS. VG is 0.833, and ID into RS is ID into 1000 because RS value is around 1000, right? Yeah, RS is 1000. So over here we'll get an equation. VGS is equal to 0.833 minus ID times 1000. That is equation number 1. Then assuming that a given MOSFET is working in the saturation region, we can write ID is equal to Kn times VGS minus VTN the whole square. Okay. And that will be 1 into 10 raised to minus 3 into VGS minus 0.4 the whole square because VTN is 0.4. Now we substitute the value of ID in equation number 1. That means we substitute equation number 2 in 1. What do we get? VDS equal to 0.833 minus 1. Why minus 1? Because 10 raised to minus 3 and 10 raised to 3 will get cancelled out and we'll get 1. Open the bracket of VGS A minus B the whole square, which is VGS square minus 0.8 VGS plus 0.16. Then we'll open the bracket and we'll get the quadratic equation. So we got VGS square plus 0.2 VGS minus 0.6733 is equal to 0. So solving this quadratic equation in your calculator, you will get two values of VGS. So one is 0.7266 volt, other value is minus 0.92. So obviously we'll reject minus 0.92 because your VGS value should be greater than your threshold voltage, which is 0.4. So that's why we select this value. Now once we got the value of VGS, we can calculate the small signal parameter GM. So GM will be twice Kn VGS minus VTN. So twice Kn is 1 milli, VGS is 0.7266 and VTN is 0.4. So the value of GM will come out to be 653.2 microamperes. Now what about RO? We have selected lambda is 0, so RO will be infinite. Okay, because RO is 1 upon lambda IDQ. Okay, so we got this small signal and the DC parameters calculated value. Now let's verify by simulation. Okay, so how to verify by simulation? So what I will do is I will close this and I'll go again over here. And here I have to comment it. Okay, and then I'll simulate this. Now they can ask, they have to select the DC operating point. Click on OK. You will get this DC operating point. You can close this and you can go to view and then you can go to LTspice log. Okay, so LTspice log will give you the actual values of all the parameters. Right, now let us check it out whether our parameter values are proper. Okay, yeah, so let's check it out. Yeah, so the value of VGS, is coming out to be, here it is 0.727 and we got calculated as 0.7266. So it's exactly matching nearly. IDQ is 106.66 microamperes and here it is 1.07 into 10 raised to minus 4. That is 107 microamperes only. GM value is 653.2 microampere per volt and here GM value is 653 microampere per volt. So all the values, DC parameters and the small signal parameter, that is GM, is matching perfectly. Fine. So in this way you can check the value of all the DC parameters. Now you can see GDS is also there. So basically GDS will be 1 upon RO, right? Now since we have given, let me write over here. GDS is basically 1 upon RO only. And here GDS is 0, right? So RO will be infinite. We have defined that already, correct? Now let me maximize the screen. Okay. So finally we got the value of GM, right? Now we'll go to, let's calculate R1 parallel to R2 also. R1 parallel to R2 is 16.6667 kilo ohms. This will come in handy. Now let's go back to our mid frequency response of CS amplifier. So this is how the circuit will look like, correct? We have R6, R1 parallel to R2, GM, VGS, RD and RL. We have discussed this many times before. If you're not clear how we got this mid-frequency response or mid-frequency small signal model, you all can refer the previous lectures on MOSFET amplifier. So from here, we can calculate V out upon Vs. So AV will be given by V out upon V in into V in upon Vs. where V in upon Vs, we have discussed this many times in our theory lectures. It's R1 parallel to R2 divided by R1 parallel to R2 plus R6. It's a voltage divider network over here, right? So V in upon Vs is coming out to be 0.9434 because R6 value is 1K and R1 parallel to R2 is 16.667K. Okay, we got the value of V in upon Vs. Next, we calculate V out upon V in. So V out upon V in, just by inspection, we are getting minus GM into RD parallel to RL, right? GM value is 653 micro, RD is 5K, RL is 10K. So the value of V out upon V in is minus 2.17733, right? That is V out upon V in. Now gain will be this value minus 2.17733 into V in upon Vs, which is 0.9434. So we are getting the voltage gain as minus 2.054. Okay, that's the voltage gain which we are getting. And if you want to convert into dB, we are getting around 6.25 dB. Okay, the value of the voltage gain in dB is 6.25. Now, if I want to calculate the output now for this particular, let's say that I don't want to keep it as around 800 millivolts. I want to keep it around, let me check what was the amplitude, 200 millivolts. Okay, so for 200 millivolts, what's the value? Okay, let me select the black pen. So for 200 millivolts, I have to do it by calculation. So you can easily calculate this number. Let me cross check in a calculator. It's basically 2.054 into 0.2. So it's coming out to be 0. Sorry for that. Coming out to be 0.4108. So that's the value of V out which we are getting. Okay. Now remember these numbers. AV is minus 2.054. AV is minus 2.054 theoretically. Minus 2.054. As you can see, the theoretical and simulated values are matching, right? And what was the value of V out simulated? V out simulated value is coming as minus 0.4108. As you can see, this is also perfectly matching, right? So our values, theoretical and simulated values are perfectly matching for this case. Fine with it? Any problem in understanding? Okay. Now let's go to the next part. Next part, what we will do is we'll remove the bypass capacitor. And then again, we measure it at, let's delete it. It should be 100 millivolt and around 100 millivolt peak to peak and around 200 millivolt peak to peak value. Okay. Fine. So let's check it. Let's keep everything same and let's check it at around. So DC analysis will remain the same if you bypass the capacitor or you don't bypass the capacitor. Okay. So let me just comment it and again uncomment my value of the dot tran and then click on OK. Then you simulate this. I have to remove the capacitor over here. I've removed my capacitor and I clicked on simulate, clicked on run. And now I can plot V out and V in. Okay. So V out upon V in, the output is slightly amplified, right? Now I'll go over here, go to view, go to spice error log, and I note down this value. Okay. So I have to note down these values. So let me slightly, yeah. So I'll note down the values of V out now. So as you can see again, V out is out of phase. So we got the value of the V out as over here. Let me show it minus 0.2471. Okay, or we can write 2472 volt. Fine. And what's the gain? Gain is around, simulated gain is around minus 1.2365. So that's the value of gain which we are getting. Fine. Now let's cross check it with the theoretical values. Yeah. Okay, this will come in simulation. This one will come in simulation. Let me add that over there. Yeah, that's the simulated value. 0.2472. Let me add it over here. Minus 0.2472 volt. Fine. Now let's check in by calculation how much is the voltage gain coming without the bypass capacitor. Okay. So if you look over here carefully, let me maximize slightly. Yeah. So if you look over here, this is the common emitter amplifier without bypass capacitor. So RS will come into picture. But that when that comes into picture, the entire this thing will change. Okay. The entire scenario might change. So over here, what do we have now? We have V out upon V in. So here we will have RSig also. I have forgot to draw that. Here definitely will have a RSig resistance. Okay. Here we can write RSig. So over here we can write V in. Okay. So V in upon Vs, we already got it from earlier result, 0.9434. V out upon V in, if you calculate it without RSig, then it will be minus RD parallel to RL divided by 1 upon GM plus RS. So this we have discussed this before. So I'm not showing you all this is your common source amplifier with source degeneration or without the bypass capacitor. So that's the formula for it. And RD parallel to RL is 3.33. 1 upon GM is 1.31. GM value is already given. So you substitute all the values over here. V out upon V in will be minus 1.3169. So that's the value of V out upon V in. So from here we can calculate the voltage gain. AV will be V out upon V in into V in upon Vs. So that will be minus 1.3169 into 0.9434. So that comes out to be minus 1.2424. Okay. So the gain is minus 1.2424. Let me write it over here. So we are getting theoretically as minus 1.2424. So that's the value of voltage gain which we are getting. And now let's check the output. So output will be Vs. Actually, this should be Vs. Let me change it, and this should be around 200 millivolt. So the value of output will change definitely. So this is Vs, and the value is 200 millivolt. So basically, we have to multiply 1.2424 with 0.2. Okay, so let's do that. 1.2424 into 0.2. So you're getting around minus, V out is coming out to be minus 0.2484 or 85 we can write, because it is 0.24848. So we can write here 0.2485. Okay, minus 0.2485 is the value. Okay, so your theoretical value is minus 0.2485. Okay, so that's how we can relate your the values, theoretical values and the simulated values. They are quite close to each other. Fine. Any problem in this understanding? So in this way you can complete for 100 millivolt also at 10 kilohertz. Fine. So this is how you will complete your calculations as well as your simulations carried out in for transient response with bypass and without bypass capacitor. All the steps are shown over here, right? So output is out of phase with respect to input. That's why we have a negative sign over there, right? And if I want to calculate the voltage gain in dB, I have to just take 20 log to the magnitude value. So that will give me the gain in dB. Now there is one thing which we have missed out. I mean, which we have done incorrectly. We'll rectify that now. Let me show it to you, right? So here we have taken Vs as 1 volt. Basically, what you can do is you can take it around at, let's say, if you are measuring it later on, if you want to cross check the value, right? So what you can do is you can take it at around 200 millivolt only, peak to peak. So these readings will change. Let me show it to you. Okay, let me change all these readings first, because that was assuming that Vs is 1 volt, but we don't usually give that much higher value because it is a small signal AC input, right? So that's why we will change these readings. We'll again simulate the frequency response at and give the input as 200 millivolt to just measure the V out value. So let's quickly do that. So for that, I will remove this dot run and I'll go back to the original dot AC. Let's quickly do that. Do not waste much time in that. And also have to put back the value of the capacitor. So capacitor is back in the circuit, bypass capacitor. I'll quickly simulate, click on run, AC analysis, type of sweep will be decade, type of sweep, okay, fine. I have to change this also input also. So this input instead of sign, I'll keep it none. And AC amplitude, I will give it around 200 millivolt. That's the peak to peak value. Fine. And now I can go to simulate, click on run, AC sweep, type of sweep will be decade, number of points will be 100, let's say, start frequency 10, end frequency megahertz. Yeah, we will get the graph, no doubt about it, but we have to measure the proper values, right? I mean, V out value. This is gain, V out, this is gain actually in dB. So to measure the value of V out, we have to change it to logarithmic scale. So now you can measure the value of V output voltage, right? So let's take some sample readings and note it down over here in our whiteboard. Fine. So yeah, let me adjust the screen slightly. Yeah. So let's test the value at around 100 hertz. So around 100 hertz, what's the value? Yeah, it's 216 millivolt. Okay, and it's unit, it's in magnitude form, 216.23 millivolt. Let's check it at around what was the next value? 10 kilo ohms, 10 kilo ohms frequency, right? So let's go to 10 kilo ohms. So over here somewhere nearby 10 kilo ohms will also do 410.75 millivolt. Okay, so 410.75 millivolt. That is the same as 0.41 millivolt. Okay, so we can even check it at a higher value at around 10 megahertz. You have to do it for all the readings, but here again we are just showing it to you. So again I'll go to around 10 megahertz. So close to 10 megahertz, I am getting 258 millivolt. Okay, so here I can write 258.04 millivolt. Okay, so now my table is complete. Why I was saying this was, let us check this value. Okay, so now okay, it's slightly taking some time, no problem. So at 10 kilohertz, what was the voltage gain and what was the amplitude of it? So let me mark it over here. It's, remember, it's magnitude, it's 410 millivolt. Okay, now let us check, go back and check the transient response. So if you go back and check the transient response at 200 millivolts at 10 kilohertz, what's the value of the voltage gain? So obviously we have taken the value of at 10 kilohertz only, and in 10 kilohertz the simulated value is 410 millivolt only. 410 millivolt is nothing but 0.14, right? So the reading is perfectly matching. So this value is verified. This value is verified in the frequency response and in the transient response. Fine. So with this we have completed all the required simulations. That is the transient response, the frequency response, and the bandwidth measurement. Now bandwidth we got from this analysis, from the simulated value, we got the bandwidth of around 8.143 megahertz. Now we have recently done a high frequency response analysis of MOSFET amplifier. So let's cross check this value by theoretical calculations. Okay, quickly, 2 minutes it will take. Okay, so let me go slightly down. Yeah, so these are sample calculations. These are not part of experiment, but you can verify this whether you are getting close to 8.14 megahertz or not. So in our case, CGS value is given as 20 picofarad, CGD is given as 0.2 picofarad, right? Let's check it out. Yeah, 0.2 picofarad and 20 picofarad. Also, let's do one more thing. Since we have changed the connected capacitor values, let's change it over here also. Okay, so here we took some different values of CC1, CC2 and CS to adjust the low frequency response, right? So here also we'll do similarly. So let me use the eraser and erase the value of C1. Then CS value also we have taken different. And then we are also taken CC2 also value different. Okay, so let's update that. CC1 value you have taken as 0.1 microfarad. So ours is 0.1 microfarad. CS is 2.2 microfarad. And CC2 value is 0.2 microfarad. Okay, so these are the values of the coupling capacitors which we have considered in a study of your frequency response of the amplifier, MOSFET amplifier. Now let's continue further. We were checking the sample calculations for verifying the higher cutoff frequency. So let's continue further. So we have now CMI. CMI is basically CGD into 1 minus AV. Now this is with bypass capacitor. So CGD value is 0.2. AV value we got it as minus 2.05, right? Let us check it out whether AV we got it as minus 2.05 or not. It has a lot of text, that's why it's, yeah. We are getting the theoretical as minus 2.05. Okay, fine. Let's continue our calculations. So over here we have CMI, which is coming out to be 0.6108 picofarad. And now the input side parasitic capacitance CI will be given, should be given by CWI plus CMI plus CGS. Now wiring capacitance are not given, so we'll assume it to be 0. CMI value is this. CGS value is 20. So CI will come out to be 20.61 picofarad. Okay. So your higher cutoff frequency of the input circuit will be FHI will be 1/2 pi R equivalent into CI. R equivalent is R6 parallel to R1 parallel to R2. So that will be R1 parallel to R2 is 16.67 kilo ohms. R6 is 1K. So you know the resultant combination will be lesser than 1K. So it's coming out to be 943.396 ohms. So you plug in the values of R6, R equivalent and CI over here. You will get the value of FHI as 8.18 megahertz. Okay. So that's the value of your FHI. Now next we calculate the output Miller capacitance CMO, which is CGD into 1 minus 1 upon AV. So AV is minus 2.054. CGD is 0.2 picofarad. Okay. So your CMO will be close to that 0.297 picofarad. Now the output side parasitic capacitance CO is CWI plus CDB plus CMO. CWI and CDB are not given, so assume it to be 0. CMO is 0.297 picofarad, and that is same as your CO value, right? So 0.297 picofarad. Okay, and what is FHO now? 1/2 pi R equivalent into CO. R equivalent is RD. Actually, it should be RD parallel to RL. And RD parallel to RL, we have already calculated before, it's 3.33 kilo ohms. So CO value we know the value of R equivalent, plug in this equation, calculate it, you will get FHO as 160.78 megahertz. And you remember what was the selection criteria for the higher cutoff frequency? So the selection criteria was that it should be the minimum of FHI and FH. And the minimum value is 8.185 megahertz. So this is my higher cutoff frequency, FH. Okay, we got it by calculation as 8.815 megahertz. Let's check what did we get at simulated value. I think we got it as 8.143. Okay, 8.143 is the simulated value. 8 point, let me check it once more. Okay. Okay. Here the calculated, sorry, the calculated is, sorry for the mistake, 8.18 pi, and the simulator is 8.14 something. I will cross check it once more. Let me do that. Okay, the pen is slightly misbehaving, so pardon for that. Let's check the simulated value once more. 8.143. Okay, 8.143. Fine. As you can see, it's very closely matching. 8.1 megahertz. As you can see, 8 pi, it's fine. Up till second digits onwards is deviating. But this is the way we can match the value of your calculated value of your fx with the simulated values of fx. Okay. So yeah, this you can try it out on your own. You can find out any numerical, whatever parameters are given, you can cross check it using this technique. Okay. So we have come to the end of this session, and we have completed the frequency response of MOSFET amplifier. We did the frequency response and the transient response, and also we measured and calculated the higher cutoff frequency. And we also mentioned, also measured the bandwidth of the system. Okay. So that will be all for this session. And yeah, thank you for joining.